music they want to listen. So that's a great challenge for us, and that's why we have a lot of data. We have a lot of data in Deezer to characterize our catalog. There are millions of tracks, millions of albums, millions of playlists, and we need to qualify them to see what kind of genre, etc., etc. We use the data obviously for recommendation. So that's most part of my part and my team, and that's why Hugo worked on this stuff. We need to crush among all along the user behavior to understand what there are and what we can provide for them. And finally, we also use the data to collect streams, to analyze them, and then to know how the user, how they behave for many purposes. I could also quote the R&D team, who has lots of work that we work with them. They made a lot of deep learning, etc., to extract from the audio data a lot of interesting feature that then we could use as a recommendation. So that's the summarize of what we use of the data, and Hugo will show you a sketch of what we do precisely on the recommendation with what we do. Thank you very much.
Okay, so welcome everybody. So I'm Hugo, and today I'm going to talk to you about the work that I've done here as an intern at Deezer, where I worked on Word2Vec methods and extensions for musical recommendation. So this work was done jointly with the R&D team and the recommendation team. I missed the... So as they presented, Deezer is a music streaming service. And here you can see our website and the iOS application, for example. And but what you can't see here is that most of the content that is presented to the user is either personalized or suggested. So, for instance, you can have personalized results in the search. You can have suggested content such as channels in the main page. And also here you can see our main feature, which is flow, a customized continuous flow of music. So obviously, recommendation is very important for Deezer. That's why we work a lot on this topic, and we use various algorithms. But tonight we are going to focus on embedding methods for musical recommendation. So first, let me define what an embedding is. So an embedding is a vectorial representation of a set of items in a low-dimensional space. So here, when we talk about items, we'll talk about tracks, albums, or artists. And but in this presentation, we'll focus on tracks to make things clearer. So here we have our low-dimensional space here in 3D, and each track will have a vectorial representation, so a point in this space. And the goal of these embedding methods will be to have similar tracks close together in that space. So when we say similar, we can think, for example, about tracks that are listened together a lot. And so once you get this embedding, you can perform recommendation. Let's say you have a track. You can look at its k nearest neighbors. Then you have similar tracks that you can use for recommendation purposes. So in this talk, we are going to talk about Word2Vec methods to create embeddings. So Word2Vec is a family of algorithms that are used in the natural language processing community to create word embeddings. So first, I'm going to present what Word2Vec is and how it works, and then we'll see how you can apply it to musical recommendation. We'll see some extensions, and we are going to go through some reasons that we've got in experiments. So Word2Vec is used to create word embeddings, as I said, and it uses the distributional hypothesis, which is an hypothesis from linguistics. that state that words that occur that occur in the same context tend to be similar. So, for example, here in the sentence "quick brown fox jumps over," if you replace the word "fox" with the word "dog," then the sentence still holds. So this sentence might appear in the data set, and then we'll derive from that fox and dog are somewhat related. And so the method to create these word embeddings with this hypothesis is to predict a word given its context, or vice versa, depending on the method that you use. So in order to do that, we are going to create a training set, then use a model and a loss function, and optimize this loss function via stochastic gradient descent. So first, we're going to create the training set in an unsupervised manner. So we are going to go over each word of each sentences of the data set. And we are going to define a window size h, so as you can see here. And within this context window, we can create positive training pairs. That means that a pair of words that do appear in the same context. So for example, fox over, fox brown, fox quick. And then we can also create negative training pairs with words that don't appear in this context window. So for example, here, big, delicious, and pizza. And so once you get these positive training pairs and negative training pairs, you can combine them to get your training set. Then you can use this training set with a two-matrix model and a loss function. And so roughly, this loss function has two terms. First term says that the embedding of the word fox and the contextual embedding of a word that appear in the context window of fox, such as brown. This term tells us that these two embeddings should be pushed together. And then this term tells us that words that the embedding of the word fox and the contextual embedding of a word that don't appear in the context of fox should be pulled apart. And that's how the model is trained to create word embeddings. So there are several tricks that are widely used in the NLP community to improve training, accelerate training, and improve the embedding space. First, you can subsample frequent words. So if you have frequent words like the or a, you can subsample them before the training, and it improves it accelerates the training. Also, you can use a random window size, so you can randomly reduce the size of the window, and it was also shown to improve the embedding space and accelerate training. And the third trick is instead of using all the possible negative training pairs, so there's a lot of them, you can sample a few negative training pairs, and you can do that by using a distribution. And we are going to talk about the choice of the distribution a bit later. And so from an implementation point of view, there are several implementations of the Word2Vec algorithms. The most popular one are GenSim and SparkMLlib. And you just have to pass as input list of arrays with your sentences to GenSim, and then you can start training and get as output your word embeddings. So now we saw that Word2Vec can be used to create word embeddings, but we want to do musical recommendation, so we want to have track embeddings. And so we used an idea from Yahoo researchers that noticed that sentences of words are quite similar to sequences of items. So you can pass as input to GenSim, instead of passing sentences of words, you can pass sequences of items, and it uses the same hypothesis. So items that are listened, bought, or used together in the same context tend to be similar. And we are going to do exactly that with listening session of our users in streaming services. So that's the Prod2Vec model. And there's also an extension of this model called Meta Prod2Vec, proposed by researchers at Criteo. that uses so the same hypothesis and an additional hypothesis that says that if you have more information on your items, you can use it to improve the embedding space. So for example, for a track, if you know its artist, then you can maybe relate this track to other tracks and hopefully improve the embedding space. So they do that by using additional training pairs that involves the metadata. So in positive training pairs, for example, what? Okay. Sorry about that. So instead of using only tracks in positive training pairs, maybe you can use track and artist. And so they do exactly that by using 4 additional types of positive and negative training pair that involves the metadata. In addition to the original one, which is the one used by Word2Vec. So for this algorithm, we don't have a classical implementation and very efficient implementation such as GenSim or SparkMLlib. And that's why we can propose to use all the possible combination of training pairs that involves the metadata. And with a simple trick, you can use the classical implementation such as GenSim and SparkMLlib. So here we can see that if you double the window size and you insert the artist ID in between each track, then if you pass this to GenSim, you'll have your slightly modified Word2Vec implementation. So in our experiment, we saw that this doesn't hurt performances, so it's a very efficient way to implement this algorithm. So now that we presented all the models that we use and studied, I'm going to go to the experiment part. So for the experiment, we used an open source dataset called the 30 Music dataset, which is composed of listening sessions from Last.fm. So in order to compare these models and try a lot of configuration with sample sessions from this dataset. So we sample a 90K session for roughly less than 1 million streams, 100K different songs, and 25K artists, different artists. So we evaluate our embeddings on an offline proxy of a recommendation task, which is called the next event prediction. So it's pretty straightforward. The goal is to, when you have a sequences of items, you want to be able to predict what is the next item in the sequence. So we split our listening session into training session, validation item, and evaluation item. Then the goal will be to, so we will look, for example, at the k-nearest neighbor of the last item in the training session. And then if the validation item appears in the k-nearest neighbor of the query item, then you'll get a positive score and 0 otherwise. So with the validation item, we bench our hyperparameters and we check what is the best configuration, and then we report as final results the performance on the prediction of the evaluation item. So first, we wanted to reproduce the results of the Word2Vec paper. So we used the configuration specified in the paper. And as we can see, Word2Vec can improve the performance on the embedding space when you use the artist's metadata. But then, as we launched lots of experiments with different hyperparameters, we saw that you can indeed have configurations where the final performance shows that Word2Vec can be best. So then we wanted to go to the bottom of this, and we saw that we were optimizing over the window size, number of epochs, and subsampling parameter. So this parameter in the GenSim and SparkMLlib are clearly stated as tunable. So you know that you have to optimize over these parameters, but some of other parameters, such as the negative sampling distribution, are often not clearly stated as tunable, and were in the first place designed for natural language processing tasks, such as word analogy, for example. So in the original paper, they saw that it worked best for NLP task, and there was several different papers that confirmed this result. So the distribution that is used is the following. So when you create your negative training pairs, you are going to be more likely to choose popular items as negative samples. And so we ask ourselves, is it the best choice for a recommendation task? We want to also optimize on these hyperparameters and see if we can gain performance. So in order to do that, we are going to change the value of alpha right here. And so with alpha equals 1, you can have a unigram distribution. With alpha equals 0, you have a uniform distribution. And with an alpha negative, you are more likely to pick unpopular item as negative samples. So here, the results. Here, the result. You have the next event prediction performance in function of alpha. And here you have the out-of-the-box Word2Vec version. So you can see that it's clearly not the best, and that you can set alpha to a negative value and have significant gains. So here are the final results. So the two first lines show Word2Vec and meta Word2Vec optimize on jointly on every hyperparameter but alpha. And we can see that for both of the models, you can gain a significant gain if you also optimize on the negative sampling distribution. And so, also we can see that the overall best performance is obtained by the Word2Vec model on this data set. So we move on to the conclusion and takeaways of this presentation. So for meta Word2Vec, we saw that you can have a really easy implementation and efficient implementation with GenSim with the following trick. Then we also saw that for Word2Vec with recommendation, with a different distribution, you can have significant gains for next event prediction. And I think that the takeaway of this presentation is that if you use Word2Vec for recommendation, then do not assume that what works for NLP will work for recommendation. You should check all the possibilities. And also, I would advise you to carefully tune every hyperparameter, including the sampling distribution and the parameters that are not clearly stated as tunable in the implementations. So for the future work, we will try to explore new offline metrics. The future goal is to have a better evaluation task, which is pretty hard. And we'll also want to experiment on other recommendation data sets to see which parameter performs best and if there is any trend that we can derive from what we learned earlier. So thank you for your attention, and if you have any questions.
Okay, so we have a question.
Hello. So if I understand very well, you used an algorithm, a machine learning algorithm, based on analysis on words and metadata. Did you study any other algorithms that involve sound and machine learning algorithms?
Yeah, sure. So as we said, in the Deezer recommendation is a very big problem and a problem that a lot of people work on. So in the recommendation team, they mostly use usage data so metric factorization and things like that. But in the R&D team, there is a lot of work. Especially the R&D team is focused on using the audio signal, and so there are current work in progress on using audio signals in order to make better recommendations, especially for the cold start scenario problem.
Do we have another question? Yes.
So is it possible to apply this technique to recommend new tracks which doesn't have any history?
Tracks that don't appear in the data set at the moment, no. It's a problem that is currently open even in the natural language processing community, if you have new words in your corpuses, you don't have any embedding for this word. So currently, no, it's not possible to use that.
But since you have this like song artist,
yeah.
do you sometimes get artist as a recommendation? No, they're like.
Okay, so in the Meta-Word2Vec model, something that's very useful is that the output of the algorithm gives you track embeddings as well as artist embeddings. So maybe you can use these artist embeddings to recommend new tracks from an artist, a new release, for example. So yeah, that's one of the big perks of Meta-Word2Vec as well.
Did you evaluate Meta-Word2Vec on more almost cold start problem? Because
that's something that we talked about with Flavien Vasile. The biggest claim in the Meta-Word2Vec paper was that it improves on the cold start scenario, and that's something that we observe, but I think not on the same scale, but it's something that we observe mostly. The most gains that you get from using Meta-Word2Vec is on the cold start scenario, indeed. So this work is useful as a research tool, but in production, using mixing matrix factorization techniques and Meta-Word2Vec for the cold start scenario seems to work best.
I'm just wondering if you test the influence of the number of tracks and number of samples, because you might have some tracks that appears really with a really low frequency, and that could bring some noise. So do you have some? Do you think that bringing, for example, artists could help to generalize sometimes? Or
yeah, that's exactly why what the negative sampling distribution does is that it balances the data set are at first very unbalanced. Some tracks do appear much more frequently than others. But the negative sampling distribution and the subsampling of frequent words is there to mitigate this unbalance in the data set.
Okay, any other question? Yes.
In music streaming apps, the next song is probably given to user automatically. So in most of the times, user doesn't select the next song by himself. And songs are given to him automatically. So there might be the case that your algorithm predicts not the relevant song, but the song that would be predicted by an algorithm you're currently using in production.
Yeah, sure. And when so we also perform experiments on our data, and that's exactly what we cared for that when creating the data sets. We made sure that we don't take any listening sessions that were algorithmically created in order to mitigate this effect. Because there are some listening sessions that are in the flow, for example, everything is recommended, so you cannot use that as usage data. We try to have some filters in order to keep only the listening sessions that are most likely to be human picked and really like coherent.
Okay, thanks.
Yeah, thank you for the talk. How far can you go inserting metadata in the sequence? Like you added the artist, but could you add the label or some genre?
Yeah, sure. That's something that we tried during my internship too. We saw that it might be beneficial, to use with the trick that we introduced. You just can insert other types of metadata, such as context, where, for example, where the listening session was listened, and we tried some of these things, and we had some good results with it, but we did not really pursue in this direction. But that's clearly something that you can do.
Okay. Any other question? So let's thank the speaker.